Sorry it's taking so long. I thought I would just do a quick video, just a quick really run through some maximum problems and some geometry stuff, just to make sure you've got something nice and clear for you tomorrow. I've written all that in your OneNote, so please check it out so you can have a look at the written stuff as well. Let's quickly chat about maximum problems. If you've done any past papers and you've already done a fair few of these, the reality is that in every question 15 or 16, in every paper that's ever been written, you're going to have to do a maximum problem. And there are really only two places where people will fall down. The first one is to create the equation that you need to maximize or minimize in one variable. This is a really important bit. Now, very often the first or second part of the question, that's what it's all about. Show that the height and the radius can be given by this, show that the area and the whatever other thing can be given by this relationship. Like, they very often lead you down that path, but sometimes it can be significantly harder to do that. It's almost always a show question, so it gives you the equation anyway, and we'll talk about that in a second. But the reality is that what you want to maximize is almost always dependent on two variables, and you can't differentiate something with two variables. So you need to find a way of eliminating one of them so that you can differentiate in terms of that one variable. So I've written it just here. The relationships can sometimes be subtle, so you've got to really carefully read the question. Sometimes they give you that relationship, but not explicitly, so be really careful there. And the three most common ones are the area and volume formulas. They give you similarity, which can be one of the harder ones, and Pythagoras, which comes up every now and then. It tends to be fairly obvious, but is a good one to remember. The last bit that everybody forgets, or where they tend to lose a mark, is of course when it is a maximum question, there is always a mark allocated to showing that it is a maximum or minimum value. There are only two options to do that. You can use the second derivative, but in maximum questions, finding the second derivative can often be incredibly difficult. So the second option, it tends to be the most common. That's a table of values. Essentially, just the setup here, you have whatever variable that you started with here in your top row, like normal. This is the first differential of what you want to maximize or minimize. In this case, I just used A, but it's volume, it's length, it's whatever you want to maximize or minimize. Then you have the actual value that you're testing. So the maximum value that goes in the middle there. And then you check a number that's slightly bigger, slightly smaller than that number. Now, the thing is, they have to be actual numbers. So if what you think your X value is 4, then you need to try 4.1 and 3.9 because this row down here, that's 0, obviously. Hopefully you've found that at 0. But you need actual numbers in those boxes there. You can't just say positive and negative, which is essentially what you're looking for. Remember that when you get those values, if you what you're looking at are the gradients of the tangents around the turning point. So if you get a positive gradient, a 0, and a negative gradient, then you have shown that it is a maximum. If you get a negative gradient, a 0, and a positive gradient, you have shown that it is a minimum. So with maximum values, they tend to be the ones you need to have a look at. I chucked a few reasonably easy ones in there, but reasonably common ones as well. This Sydney Girls one is a classic one, very, very common. You can see here that show the length of the pipeline in total is written here in one variable, and it's worth 1 mark, so this was a relatively easy one. Okay, of course, the length of the pipeline up here, you can read it. I'll let you have a crack at this one on your own. But you can see here the additional mark here, you've got to be a little bit careful. But essentially, you have now a function for the cost in terms of one variable. So now you can do a differentiation. Find where P should be located to minimize the cost. Be careful, P in this case is a value of X, so you're actually finding X, but sometimes it could ask you, for instance, for the length of PS, right? So you got to be careful, you make sure you're answering the question. But that's just you differentiate, find the value when it equals 0, and then show that it's a maximum and minimum. Another nice little common one here is the cone. This is a different take on the cone. One, you should have seen a cone inside a sphere or something like that very, very often. Here you've got just a couple of little relationships. They make it a little bit harder. But you can see here already, they're teasing you with the idea of taking one variable and then writing it in terms of another. Okay, and then you can see here that the volume ends up being in just one variable in this particular question. H is a constant. And then they give you everything else, right? They give you another relationship here, okay, down here, and now you can get rid of all the variables that you need. And so it's a slow build up, that one. It's an interesting one. I'll let you try that one before you have a look at the solution, which is on the next page. And then in Cranbrook 2016, the question 16, you'll be stunned to hear that I wrote this one, so I'm reasonably proud of it. But the whole point of this one was to make an equation that was difficult to differentiate, but gave a really subtle link between the variables. So I'll read this one out. A radioactive liquid known as sadlarium emits a constant red glow. The intensity of the glow depends on the dimensions of the container in which it is poured. The light emitted, E, from a cylindrical container of sadlarium is given by the equation log of 1 over 10A minus H on 10 plus 50, where A is the circular base and H is the height of the cylinder in centimeters. 3 liters of sadlarium is being used to create a cylindrical lamp. Now, let me tell you that almost everybody who lost a mark in this question lost it because they missed that particular bit. There's a huge issue with this. It has 2 variables, an H and an A. So at the moment here, we cannot figure that one out. We can't differentiate that. And so to jump to this 1 mark, just 1 mark here, right? We seem to be writing it all in terms of R. So we take A equals pi r squared, that's pretty straightforward. But then what's the relationship between A and H? Of course, if you have 3 liters, it means the volume of your cylinder, pi r squared H, must be equal to 3. And now you have a way of replacing H from this equation with R, because you've got this relationship here. So in this particular case, the differentiation was also quite difficult. It was a question 16. I made it purposely quite challenging, but or like that, the worst performance was actually in part 1, because almost everybody missed that 3 liters part. So keep that in mind when you're going through it. Maximum problems are definitely going to feature, and they're just a couple of little tips. Hopefully you've got most of them under control. You can see here that on the next page, you've got the solutions to those. Just another little tip about geometry. As I said, this is the last year for geometry, so geometry will almost certainly feature pretty heavily in your actual HSC, and of course the trial tries to mirror that, so you can expect some sort of geometry, of course. There's 2 parts. If you get one in question 11 to 14, then you've got an easy one. This is pretty much just a standard congruence or similarity proof. Okay, make sure you've got nice structure to it. Make sure you give you nice reasons. Make sure you explain them nicely. It doesn't have to be word for word perfect, but pardon me, they have to be full sentences. So please make sure that you're giving those. Then you get the hard ones. Now, so there's really 2 parts to a hard one, like 2 things that make them hard. The first one is just using similarity to show that a particular ratio through an intermediate. So not directly showing a ratio, or 2 things are in or 4 things are in a particular ratio, or the product of things are equal, but rather going through an intermediate. And you can see here, right, okay, so this is a very, very straightforward example, but we've got ST times QU is equal to PQ times TU. So they're not in any triangles at the same. So you've got PQ over here, you've got ST up here, you've got QU over there, and you've got TU over here. The first thing you should always do is never leave it as a product, but rather put all the ratios from the same triangle together. So in this case, I'm going to put PQ over QU, and that of course would mean that we are equal to ST over TU. Now they're not in any way similar triangles, but actually what you end up doing is proving that proving this relationship here, so proving that triangle and that triangle are similar, and then you can prove pardon me, that these 2 triangles are congruent, and then you just replace it, right, which is essentially the working over here. So they don't have a direct relationship, but we use similarity or congruence to create that relationship through an intermediate. Okay, so be on the lookout for that. And then there's this classic one, right? Parallel lines cut transversals in fixed ratios. It just seems to pop up all the time in these sort of harder geometry ones because no one ever remembers it. But essentially, if you have these parallel lines, which I've done here, which are drawn incredibly poorly, any pair of parallel lines, you actually need 3, but you get what I'm saying here, right? Any pair of breakages in those transversals are in a fixed ratio. So I've given you a few examples here. In green, I've taken the top of these 2 here, so AF and AG, as well as FB and GC, and they are in a fixed ratio. AF on FB is equal to AG on AC. But I can use any combination I like. So here with the blue, I just took the longer ones, AC and CE and AB and BD. But then you can also take the ones from the middle, which I've done here in pink. where I took GC and CE and FB and BD. All those in a ratio with each other. The reason nobody remembers that is because you do it as a very quickly in year 11 and then you never look at it again. But it does pop up in those harder ones. I grabbed an example here that I've figured out for you where you use that particular one. It's not a particularly difficult question once you've got the solution, but of course, thinking about it makes it very difficult. That's actually the last question of the 2017 HSC, and it wasn't done particularly well. So have a look through that one. Make sure you're just going through your geometry rules. Really keep in mind that last one, but hopefully that'll all stick in there. I'll see you guys in the morning with a little bit more advice, but good luck.